So let me get around here. Okay, greetings, class and YouTube watchers, because this video is going on YouTube. So if you came in after I said the following thing, be wary. Don't get your image taken. Just for your privacy, it's just me. Okay?
But feel free to ask questions.
Oh yeah, ask all the questions you want. Just don't become part of the video because it's a privacy thing. Okay, so today we're going to talk about the Planck Scale. This is our first lecture of the semester, and it's part of a sequence I've put together that will gradually get us to larger and larger things. You know, last time I was here, we talked about the scale of the universe as a way to organize how we're going to talk, and I drew a line like this, and over here, the Planck scale is here, the smallest sensible dimensions in the universe, and over here, 44 billion light years. That's the physical size of the universe, and of this we can only see about a third is available to us. The rest has gone over the horizon as the universe has aged. We'll talk about this. But the age of the universe that we can see is a third of this, about a third, 13 billion. But we're going to talk about this end of the scale today. So there is, and this is kind of a mysterious part of physics, is what are the smallest things we can talk about and have sensible physics. So 1900, this guy, Max Planck, struggled with a problem that had been perplexing physics for a long time. Once people started being able to measure heat waves, or infrared radiation, from things like glass furnaces or steel mills, they actually made measurements of how the properties of that heat radiation, and they got this kind of curve. Here's wavelength. If you haven't had wavelengths in physics, how many people are not familiar with the concept of wavelength? Okay, so right here, Sophie, how did I do? Paris?
I'm Sophie.
Sophie, I was right the first time. Right here is the visible wavelength spectrum our eye is sensitive to. The sun is peaks kind of like this, around 6,000 Kelvin. So it has a lot of yellow and appears white to us because of the way our eyes have evolved. But this is wavelength, meaning what is the size of the waves, the electromagnetic waves that we see. And these curves were measured relatively crudely starting in probably the 1870s. But gradually the measurements got better and better, and theories evolved about why does this curve look the way it does, with a peak in the middle, and you can see it's not a balanced curve, right? It has more energy over here than it does on this side. And this guy, Max Planck, struggled with this problem and eventually figured it out by using an extremely bold and insightful calculation, and he produced this equation. He didn't just write it down, he actually derived this equation. This is what's called the black body radiation formula. And I'll point out some parameters in here. Here's the wavelength, that's the same as this Greek lambda. There's a thing here called Boltzmann's constant, which is a common parameter in anything having to do with heat. T is temperature, C is the speed of light, and lo and behold, after Max Planck got done with his calculation, he matched the shape that had been measured for the black body radiation from a glass furnace or something, like even a fire, a pile of burning wood produces a spectrum very much like this. But to get the peak of his calculation to match the peak of the measured radiation, he had to introduce this parameter, now called Planck's constant. And by adjusting it, he got the data from measurement and the theoretical calculation he had done, he got them to match. And this value is equal to this number. It's a tiny number, 10 to the minus 34. And so it appears here as an H. Over here I've written it with H with a little line crossing the H. That means it's it's this divided by 2 pi. That just simplifies the arithmetic when you're doing quantum mechanics. But this is the scale of Planck's constant. And almost immediately Planck realized that he could invent units of time, energy, distance, power. I'll show you all these things in a minute. That he could invent units using something called dimensional analysis. We're not going to go into that today. So here are the parameters he used. He mixed together principally these 3 parameters. Speed of light. Everybody should be memorizing 3 times 10 to the 8th meters per second. Gravitational constant has these units, 10 to the minus 11. That's Newton's gravitational constant, the reduced Planck's constant, which is Planck's constant divided by 2 pi. There you see it there. And by mixing these things together, we can, and there's Boltzmann's constant I already mentioned. And so he was able to construct a system of units. What I mean by units: length, mass, time. We use kilograms, meters, and seconds. But by juggling these things, as I'm about to show you, you can come up with what he called universal units, and you can form a system of dimensions with this. And it's been proposed that if we want to really communicate with alien civilizations who are savvy enough to send signals to us, you won't want to do it with kilograms, meters, and seconds, because those are each a dimensional scale that we invented. Alien civilization might have invented a different scale, but they can't get around this, because these are if you mix these together the right way, you get constants that would be true anywhere in the universe. Okay. So what is the Planck scale? That was the title of this lecture, and it's the spatial time or energy scale where what we know about physics fails. So classical physics explains how cars operate and how a billiard ball rolls on the table and so forth. Quantum physics talks about tiny things, atoms and subatomic particles. The Planck scale defines an area where physics doesn't have a defensible theory. So let's do an example. The Planck length. Now, you notice I sometimes pronounce it Planck and sometimes Planck, which is the German pronunciation. So I apologize. I flip back and forth. Stepping out of the picture for a second. Okay, so here's what I mean by mixing together the parameters. If you want to get a Planck length, here's what Max Planck did. He took his constant, which has certain units, Newton's gravitational constant, and the speed of light cubed, and if you do that and take the square root, you get the units of meters. And you're going to see before we're done with this little lecture that there's all kinds of ways to juggle these 3 parameters to get things that are commonly used in physics, like energy, power, distance, area, volume. They're all expressed in this form, just 3 parameters. Sometimes we add Boltzmann's constant to do thermal things. So what is the significance of this? That is a tiny number, 10 to the minus 35 meters. That's 10 to the 20th times smaller than a proton. And the thinking is that at this spatial scale, physics has no meaning. That you can't define a sensible physical description of this spatial scale. It has to do, well, so let me diverge for 1 second and mention, it has to do with something called quantum foam. If you, and I've said this to others who have been in this class in the past, if you make a vacuum, take a box, here it is, pump all the air out, and you could say, I could hand this to Sophie or Paris and say it's empty. But that would be wrong, and they would say, that's not true. There's all kind of virtual particles appearing and disappearing inside this box. They last a very short time. I'll show you how short in a second. They're just bursting in because of something called the uncertainty principle. They're being created and destroyed all the time. This room is filled with virtual particles. Some people call that quantum foam. And the spatial scale and temporal scale in which that happens is part of the Planck scale. So here's the Planck distance. It's super tiny. So we haven't proven this. Nobody has measured this. It's too small. Oh, here's a reference to quantum foam. So if you get the lecture notes from Mr. Hankla and click on that, you'll be thrown into an article about quantum foam. Okay. Any attempt to investigate shorter distances than this, you end up having to have so much energy to explore that tiny little space that you'll create a black hole, and there's no physics to be done. So on this scale, anybody would like to venture a guess about where a black hole goes on this scale? Yeah, it's off the scale over here. Black holes, the people think about them as astrophysical objects. They are objects. They influence the motion of stars in their vicinity and so forth. But they're the tiniest things in the universe. They're tinier than the point of a pin. They're tinier than a piece of an atom. Because it's a gravitational collapse has occurred. So in order to generate enough energy to explore this regime, you just make little tiny black holes. And there's nothing to see there. That's what the police say when there's an accident. Nothing to see here, just be on your way. So now we can also square this dimension. Remember, this is in meters. You could square it and you get Planck area. And that's related to an interesting property of black holes we're not going to talk about today, and that is how black holes behave when you put information into them. Information, a single bit of information increases the surface area of a black hole by this increment. It's one of the big discoveries. Bekenstein discovered that when you talk about information storage, if you throw a copy of the encyclopedia into a black hole, the black hole gets bigger as you put some mass in. You put information in, but it doesn't get bigger in terms of a volumetric sense. Its surface area gets bigger. Oh yeah, Bekenstein, there he is. Okay, and this relates also to something called string theory, which we'll talk about later in the semester. So here's a way to think about how stupendously small that is. If you take a dot, 0.005 millimeters, that's 5 microns. A dot 5 microns in size on a piece of paper. It's hard to see it. But if you take that and expand that dot to the size of the current universe, so make it so it's 13 billion light years, that little dot. The Planck scale that was present in the original little dot in a piece of paper, that is now equal to this size. It's still very hard to see, even though you've taken this and scaled it up by billions of light years. Okay, so that's Planck distance. Planck time. Look how tiny this is. 10 to the minus 44 seconds. Yes, sir.
So, are we saying that space is quantized? Time is quantized?
Maybe. Maybe. But the theoretical understanding of this scale is immature. Thinking of the Planck volume as something like take a grain of sand and shrink it down 55 orders of magnitude. Is it the smallest volume? It's really about do we have a sense of does physics work rather than is it quantized. All right, so here again, take a look. Remember the last time we had h, g, and c cubed in a square root. Now we got a c to the fifth, and out of this mixture of units, and this is something you can do yourself. If you look up Planck's the units of Planck's constant, Newton's gravity, and the speed of light, they're all at the beginning pages of this lecture. Mix them together and take a square, you'll find that you get units of seconds. So, but incredibly short time. Now what does that mean? This is the time it takes light to travel the Planck distance. Okay, so if you have we already agreed the Planck distance is extremely tiny. The time it takes light, going at the speed of light, to cross that distance is this tiny, stupendously tiny number. Right? And once again, this is where some kind of new physics, possibly quantum gravity, which is a...
So that's speculation at this point?
Yeah.
Okay.
So, and the idea is that at times shorter than this, nothing can happen in the universe that affects the behavior of the universe. It just is meaningless to talk about time shorter than this. And so now let's talk about mass and energy. Here is the Planck energy. And once again, it's a simple mixture of three parameters we've already talked about. In this case, the speed of light is in the numerator, and you get units of joules, which is the units of energy, or electron volts, and this is the European style for billions. 10 to the 19th billion electron volts. That's the Planck energy. Now, let me remind you of something. The Planck distance is incredibly small compared to us. The Planck time is incredibly short compared to anything we experience, but this is a big number. This is a bit of a mystery. I'll show you more about this in a second. 10 to the 9th joules is about how much energy is in a automobile gas tank when it's full of gas. So instead of being microscopic, like the Planck time and the Planck distance, Planck energy is what we call macroscopic. If we had a tank of gasoline and we blew it up, we'd all want to step back. It's a human scale big deal. So the question is, how do we convert from the Planck energy, this, to the Planck mass? Because there is a thing called a Planck mass. So we're going to use this, E equals mc squared. So the mass, the Planck mass, is equal to the Planck energy divided by c squared. We do a little bit of algebra there. I'm not going to fill this in. While I'm talking, see if you can figure out what that is while I'm talking. Okay, so Planck energy is big, and the Planck mass, which you are busy calculating in your head right now, is about the size of a flea's egg. Very, very small, but not, I mean, with a proper microbalance, you could detect the Planck mass. And the Planck mass is that's backwards. It's 10 to the 19th times larger than the proton mass. The Planck mass is 10 to the 19th, that's a huge number, compared to a proton. So once again, the other Planck parameters we talked about are extremely small. Planck energy is a real world thing. I mentioned about the same amount of energy as a tank of gas. And so here's a way to think about what this means. If you confine the Planck mass, that's a way to talk about it. Oh, sorry, here, whenever that thing pops up, you'll see it. If you confine the Planck mass to the Planck volume, how do we get the Planck volume? It's the cube of the Planck length. If we put that much energy, or mass, they're equivalent, into a Planck volume, you get a black hole. And there are probably some of those in this room right now, being created by virtual processes, appearing and evaporating in very short times. So, how about this energy, the Planck energy, and compare it to what we, particularly this, what we have at the biggest research facilities that do subatomic research, like the big one in France and Switzerland, CERN. If you guys are interested in this, you should learn about the European Center for Nuclear Research, spelled in the French way, so the order of letters is a little different. CERN has a big accelerator, but theirs is 10 to the 15th times smaller than the Planck energy. So if you want to create a Planck particle in a big accelerator, you got to figure out how to increase the power of the biggest machine we currently have by an order of 10 to the 15th. which is a tall order. You need an accelerator the size of the universe, approximately. All right, so let's see. So here's, if you take this Planck energy and divide by c squared goes into the square root. Do a little manipulation there, and you get this expression for the Planck mass, 10 to the minus 8 kilograms. So this is kind of interesting that the Planck energy is big compared to things we're familiar with. Oh, yeah. So this is the Planck mass right there, 10 to the minus 8. For a lot of calculations people do in general relativity, and we'll touch on this later in the year, it's more convenient to have this form. That 8 pi is a common expression or a common part of equations in general relativity. So if you put it in here to reduce the number of times you have to write 8 pi, you get a slightly different mass. It's this with the 8 pi in there. It's just a convenience. But still, tiny mass, but when you multiply it by c squared, you get big energy. How about Planck temperature? It is possible to define the Planck temperature using the 3 parameters we've been talking about and Boltzmann's constant, and it turns out to be 10 to the 32 kelvins at the highest temperature you can imagine. And I believe, I calculated this for a class prior lecture, that when a black hole evaporates, the last bit of it that comes out of the black hole as the black hole disappears has this temperature. So we'll talk about black hole evaporation. It's also, if you have a black body at this temperature, the peak of its radiation has a wavelength equal to the Planck length. This is and this might have existed in a very early universe, as the universe was, billionths of a second right after the Big Bang. Temperatures were really high, like in this vicinity. But once again, we don't know much about this. This is probably requires a big advance in theory in the area of what's called quantum gravity. So here's how you calculate the Planck temperature. Once again, it's simple. It's a square root with the 3 things we've been using, and Boltzmann's constant is in there. Put those together to get this result. This you can measure in a thermal physics lab. So here's an interesting application of Planck units. Turns out, if you're studying stars smaller than about 1.4 times the mass of our sun, when they, depending on their chemical makeup, their constituents, they can become what's called a white dwarf star. And the white dwarf is just a quiet thing that gradually cools down. But as long as its mass is less than 1.44 times the mass of our sun, it won't undergo any more transitions to supernova or other kinds of exciting things that happen in stars. And this theory was developed by Chandrasekhar, an Indian working in the United States, at the University of Chicago. In the 1930s, he worked this out using the rules of quantum mechanics. There he is. And here's what he got, that the mass, the Chandrasekhar mass, 1.4 times the mass of the sun, has this formula, and you see some similarity to what we've been talking about. There's Planck's constant, speed of light, mass of the proton, Newton's gravitational constant, and you cube that and take the square root, and you can write this another way, that you can write it like this. The cube of the Planck mass divided by the square of the proton mass, and you get that same answer. So there's some relation between this result, and I wrote 1.5 there, it's 1.45 or something. that and that are supposed to be the same number. But here is an elegant way to express that mass as a ratio of the Planck mass to the proton mass. And so you'll find if you talk to professional astrophysicists, they have all kinds of uses for the Planck units to simplify the results. Rather than writing this, they can write this simple form here. So let's look at some other things, some other mixtures of these three parameters that give us. So we already talked about the fact that the Planck area is the square of the Planck mass, the Planck length, and it's this, it's hg over c cubed, and it's tiny, 10 to the minus 70 square meters. But then we have the Planck volume is the cube of the Planck length. Here it is. Momentum looks like that. See the similarities here? Many of them have square roots. Force, this is interesting. The Planck force is equal to the fourth power of the speed of light divided by Newton's constant.
Force.
Power, some of you who've had physics understand the concept of power. Density has units of, the way we do it, kilograms per cubic meter. How much mass is in a volume? Here is Planck density, energy density, intensity, pressure, acceleration, and so forth. In fact, here's the Planck acceleration, c to the 7th divided by hg under a square root. And there you can look around, you can find big tables, virtually everything in physics expressed in using these three parameters, hg and c, and sometimes Boltzmann's constant. And I think that's the end of what we're going to talk about. So we got about 5 minutes for comments, questions. Sometime maybe later in the semester I will repeat my lecture on dimensional analysis and show you how this is done. And by the way, dimensional analysis is the technique Planck used to derive his version of this back in 1905 or something. And I don't think at the time he understood that this might have, that scales like this, very short times, very short distances, and modest size energies would have any relevance in physics. In fact, I saw this week in one of my classes at the university a comment from Einstein talking about, he wrote a letter back in the 1930s explaining how you could find planets going around distant stars using the fact that mass bends the trajectory of light that comes near it. And one of the sentences in his little paper was, of course, we will never be able to do this. Astronomers will never have techniques that allow us to see this effect. Well, in fact, we do now. I'm taking a class at the university now on planet detection, and they showed data yesterday, in fact, of something called microlensing. So when a planet gets between us and a distant star, for a brief second, we see that distant star get brighter. And the fact that it gets brighter and then gets dimmer again can mean that an object was right on the line. So all three of us were in a straight line. And that's a technique used to find planets. Yes, sir?
So Planck and Einstein were kind of doing their stuff around the same time. Did Planck use E equals mc squared to derive the Planck mass, or was that?
No, he didn't have to. He didn't use E equals mc squared. He used the fact that the units of mass it's inevitable that you will get his, sorry, I went back too far. What we want is that, we want this, that if you want to get mass out of this set of parameters, it comes out this way. The fact that this is true didn't happen till, Einstein didn't show that till 1915. Yeah.
So, I mean, all of this just feels kind of arbitrary. You know, you're fiddling around with constants until you get the units that you want. Do these equations, like the square root of h bar c over g, does that come out elsewhere?
Well,
in,
let me...
in a context that it's useful? Because this feels like we're just fiddling around.
Okay, all right. So here's I think a good way to think about it. If instead of using kilograms, meters, and seconds in units back in 1900, if Planck had, if all of physics had been using feet and seconds and some measure of mass like slugs, and each of these numbers would have changed. I mean, the speed of light is 186,000 miles per second. So if you were committed to speed in miles per second and mass in slugs and so forth, you would have had, these numbers would have been different, but this formula would be exactly the same.
Right. No, I get that.
Well, that's
what
the
I'm
profound
saying is did Einstein come up with, for example, when he was studying relativity and came up with E equals mc squared, that this square root of hc over g has some physical meaning?
Probably not at that time.
Okay, or has anybody since? I mean, I just...
Yes.
You know, we come up with these numbers, and from fiddling with the units, and I just don't have any sense that they have any physical meaning. They just seem arbitrary.
Well, if
Yes,
I give
I
a
get the
talk
ratio.
on string, if I give a talk on string theory, you'll see this.
that comes up.
Yeah. Just
And-
like
independently of just fiddling with the units.
just like this comes up in string theory, that the sum of all the natural numbers equals -1/12.
Okay, you're explaining something arbitrary with something incomprehensible.
So yeah, this is all over the place in,
Okay.
in string theory.
Okay, so all right. Do you see what I'm saying, though? I mean, I can combine the units of, you know, acceleration and mass.
Well,
Just
as long as you,
what meaning
that is true, but if you want to have a constant that relates the forces induced by gravity, you will have you will inevitably have a constant.
Yeah.
Or you can have natural units where g equals 1. And in fact, in most cases where this kind of thing is applied, c and g are set equal to 1. Because, so for those who haven't seen this before, I know we're almost out of time, but I could have this as Newton's law for gravity.
In the right unit system.
If you pick the definition of mass and distance properly, you don't need to have a constant.
That's true. Yeah, what's that, Gaussian units or ESUs?
Or it's SI or they're
I need to
Okay.
set up the next one.
all right, time for a new class.
Thanks, Ed.
Thanks, everybody.